Greetings, students. Okay, so we're going to continue today with our discussion of ADME and pick up with drug distribution. Here's our little diagram that relates to various ADME processes. And you can see we've already talked about what happens after a drug dose is given when a drug is administered. It has to go through this initial process of absorption in order to begin to fill the blood, the central compartment. From this point on, though, the drug gets to the various components of the body, the tissue, and the receptors, the liver for biotransformation. Some of the drug is excreted. All these other processes, all these other parts of ADME really occur with respect to this central compartment. Now, I have the question here below. Once absorbed, how does a drug know where to go to elicit a pharmacological effect? For example, let's say we have a drug for headache. How does it know to go to the brain? Well, I hope you can sense intuitively that a drug is just a molecule. It has no idea where to go, what the site of action is. It just goes essentially where the blood takes it. So the blood obviously carries the drug through capillaries, through the vasculature. And that's our point of reference in terms of drug distribution. So we're going to be always referring to these capillaries. And you see that drug can come out to the site of action. It can come out to liver, various places, but the frame of reference is always the capillary. And I do want to say that, kind of give you a little bit of a working definition. Drug distribution is the movement of drug molecules from the blood to and from the tissues of the body. So let's talk a little bit more in detail about what distribution is all about. And basically, distribution, as I say, is taking the drug from the blood to tissues. This is almost always a downhill process, which is generally, if you think of it, not a problem because the concentration gradient is such that the drug is much higher in the blood than it is in the tissue, at least initially until you reach some kind of steady state. So that's generally the transport direction. Now the capillaries are sort of the functional unit of this distribution process, and this is a little confusing. So try to kind of follow what I'm saying here. Most capillaries are what we call leaky. Okay, there's a space between the individual cells of the capillaries, and this leaves a bit of a gap between the cells through which small molecules can pass. Okay, and when I say most capillaries, I'm talking about muscle, fat, liver. Okay, for example. Now, on the other hand, there are capillaries of specialized organs. Okay, that have what are called tight junctions. The individual cells of the capillaries are contacting each other, so there's no gap in between the cells, and those capillaries are found in very particular tissue. Brain is the #1 tissue where there's tight junctions in the capillaries, but also the testes, the eye, and the renal tubules. So the blood vessels that perfuse all these organs have tight junctions, and renal tubules are important. We're going to be talking about that a little bit later when it comes to drug elimination. Okay, so it's worthwhile knowing these tissues as specialized organs with tight junctions. And this is just a diagram showing you in a little bit more sort of cross-sectional representation of a capillary, and you see that the endothelial cells don't quite touch each other, and you have these spaces in between. whereas something like a brain capillary, the endothelial cells have tight junctions. And there's additional components to the barrier. There's these lipid-like astrocytes which surround the capillary endothelial cells and really, particularly in the brain, restrict penetration of polar molecules unless, again, there's a transporter. So let's look at a diagram of what this kind of looks like. Now, I know it's just a cartoon, but it does a pretty good job. Okay, so if we take a typical capillary, so this could be, say, muscle or liver, and we see we've got two kinds of molecules here, ionized or polar molecules and lipid-like, lipophilic drugs. So let's take a ionized or a polar compound. Well, notice that that compound that's inside the capillary, in the blood in the capillary, can get between the junctions, but it can't get through a cell. Okay? So it can't get through the cell, but it can get between the cells. And then a lipid-soluble drug, on the other hand, can either get between or through a cell. So another thing I want to point out is the answer to this question: what is different about the structure of the capillaries compared to the anatomical barriers for absorption? Remember, when we're talking about the skin, the lung, the gastrointestinal tract, basically those all have tight junctions, so that you can only get lipid-soluble drugs to be absorbed. So it's just something to keep in mind. Now, getting back to capillaries, okay? The capillaries of the specialized tissue, okay, have these tight junctions, and it's represented here by these black bars, okay? So that if you give a polar compound, now the polar compound, you see, which is in the dark here, cannot get between the cells, and it can't get through the cells. So it basically can't get into those tissues. Now, there is an exception here. That is, if there's a transporter indicated by a T. But in terms of passive mechanisms, these polar compounds basically are trapped in the capillaries of cells that have tight junctions. On the other hand, lipid-soluble compounds, lipophilic compounds, can get through the epithelial cells. So let's look at factors that affect drug absorption. Well, the two biggies are the drug size, or the size of the molecule, drug or not, and the polarity of the compound. And also, of course, the structure of the capillary. Is it typical or specialized? Does it have tight junctions or loose junctions? Blood flow is also an important consideration, but we're going to be talking about that more quantitatively in your pharmacokinetics class. So what is there about distribution that affects, what is there about the drug structure that affects its distribution? Well, we have nonpolar molecules, as I said before, can cross through or between capillary cells, whereas polar molecules can only get between capillary cells, and even then only if they're relatively small. Now, I show here molecular weight is greater than 1,000 is when you cannot get through a capillary cell. So for most drugs that have molecular weights that are like in the 500,000 range, 500 to 1,000 range, they are the small molecules that can get in between capillary cells. So just to really beat this to death, let's try to fill in this table together. So we're going to look at tissue penetration of various substances, okay? And we're going to start the first row with a polar substance that is a small, molecular weight about 500. So would that penetrate into muscle? Now keep in mind that muscle are the loose junction. Typical capillaries with brain is the tight junction. So polar molecule, small, can it get into muscle? Well, remember, it can get in between those capillary cells, so the answer is yes. How about into brain? Well, it can't get through the cells, and it can't get between them because there's no, they're tight junctions, so no, it won't get in. Now, what are some examples? Well, sodium ions, believe that or not, even though they're small, they cannot in and of themselves get in many drugs. Now, sodium ions do in fact get in, and the way these things get in, the way the polar substances get into the brain, is through specialized transporters. Okay, so now let's look at polar large molecules. Well, can they get into something like muscle? Now remember, these have to fit in between the capillaries. So if it's a big molecule, no, it can't. And we already know that these polar molecules cannot get into brain. What are some examples? Well, the one I want you to keep in mind, because it's useful to know later, is albumin. Albumin is a protein, about 4% of the plasma is albumin, large molecular weight about 40,000, and a very polar compound. And that is retained within the capillaries of the vasculature all over. Okay, so now let's move on to the next row here, nonpolar compounds. Okay, so lipophilic compounds. So in this case, we're just talking about small molecules because there really aren't too many large nonpolar compounds of interest. So let's talk about small or medium-sized nonpolar compounds. Can they get into muscle? Well, of course they can. They can either get through the cells or between the endothelial cells. So the answer is yes. Can they get into brain? Well, they're nonpolar, so of course they can get through the capillary cells. And what are some examples? Lipophilic drugs. Ethanol is an example, ethyl alcohol that easily penetrates into the brain. So I hope you can kind of put the fill in that table on your own, especially with respect to whether or not polar small or large molecules would be able to penetrate into representative tissue, such as shown here. So here's a slide that would be. This is a good point for you to kind of look over these questions and see if you can answer them based on what we've talked about already. We'll discuss these questions more in class. So let's give an example of a real drug substance and talk about its distribution. Here is the structure of penicillin G, okay, and it's shown here in its ionized form as the acid group in the carboxylate versus the protonated form. But whether or not, certainly the ionized form is polar, but even the protonated form, you can see, look at all these heteroatoms, sulfur, nitrogen, oxygen. This is a very polar compound. Okay, so I think it qualifies to be called a hydrophilic polar compound. As I said before, it's also extensively ionized. So the question is, would this be something that is likely to be able to get into, say, muscle? Well, again, if you go back to our chart that we previously went through, sure, it can get into muscle. It can go between the cells of the leaky capillaries of the muscle. Could it get into brain, for example? Well, now that's a different story because it's a polar compound and it wouldn't be able to. So indeed, getting drugs such as antibiotics into the brain for people who have encephalitis and meningitis brain infections is a challenge because many of these compounds are polar and they do not easily distribute into brain. Now, we spoke about albumin before. Albumin is a compound that is a protein that's in the plasma, constitutes about 4% of the plasma. It's a large molecular weight, and it itself, this is the thing to remember, does not escape the capillary in normal situations. Okay, as long as somebody's healthy, their albumin is restricted to the vasculature. Okay. Now, the thing to remember is if a drug is in some way associated with bound to albumin, it itself then functionally becomes like albumin and is not, at least while it's bound, is not allowed to partition outside of the capillary. It stays then with the albumin in the capillary. And many drugs are, we call them bound, protein bound. You'll hear that expression. But I do want you to keep in mind, please, that this is a non-covalent interaction. You can kind of think of it like dating. The albumin molecule and the drug molecule, like a guy and a gal. Sometimes they're together, sometimes they're not together. Not like they're married. Okay, that would be more like a covalent bond. This is just a loose association where we're taking a snapshot at any point in time and we can say, okay, at this point 99 molecules are bound and one molecule of drug is not bound. And then if you take another snapshot 5 minutes later, you still see 99 molecules bound and one non-bound, but the one that's non-bound is a different molecule. Okay, so it's a reversible kind of binding. And this association, this snapshot that we might take of a protein and a drug is variable. The extent to which that binding occurs is variable, and it can range from 0 to 100%. So here's just to kind of give you an example of what I mean. Diclofenac is a compound. It's an acidic compound. It has a very high protein bounding, 99.5%. Okay, so if you had 100 molecules of diclofenac in plasma, 99 of them, or we might say if we had 200 molecules in plasma, out of the 200, 198 of them would be associated or bound to albumin at any point in time, and 2 molecules would be unbound. Okay, and that goes all the way down to aspirin here. Aspirin, you see 50% is bound. So I think the other take-home message here is that many drugs are associated with plasma proteins. Okay, but the percent binding varies. So who cares about plasma protein binding? What is the functional consequence of it? Well, for one thing, again, when a drug is highly protein bound, it cannot distribute out of the capillary into the tissue. So you restrict its distribution. The other thing is to keep in mind. So that, for instance, if we had an antibiotic, it would as long as the infection is only in the vasculature, even a drug that's highly protein bound wouldn't matter. It's working inside the blood, it would be fine. However, even in that case, it's only the unbound fraction that is available to interact with a receptor. So even within the blood, it's only the unbound drug, in the case, say, of an antibiotic, that would be able to interact with the microorganisms. So not only does high protein binding restrict the distribution, that is the penetration in the tissue, but also the activity of a compound. So please keep this in mind. Only unbound fraction interacts with receptors. And lastly, and we're going to talk about this more in depth later, the excretion is somewhat restricted by high protein binding. Compounds that are highly protein bound are not filtered at the glomerulus, so they, just like the albumin is not filtered at the glomerulus. Okay, so the drugs that are bound to proteins, then that it tends to prolong their half-life, if you will. And that's again only for drugs that are highly protein bound and that are excreted in the urine. Now this is a little bit confusing, so try to bear with me on this. But the point here is to show you that the effect of plasma protein binding on distribution of a drug into the brain. So assuming a compound is lipophilic enough to get through that brain capillary, okay, how much of it would be in the CSF? if you kind of let things go to a steady state situation. Well, the thing to keep in mind that in the CSF there's not any albumin, so you only have free drug in the cerebrospinal fluid. So on the plasma side, you have free drug and you have bound drug. So the bound drug in this case is 9 millimolar, okay, in equilibrium with the 1 millimolar free drug. So this is a drug that is roughly 10% protein bound. Only the free drug is able to equilibrate with the CSF. So I always kind of keep in mind that generally speaking, if there's not an active transporter which is driving this equilibrium one way or the other, if we're just talking passive mechanisms or just facilitated diffusion, the concentration of a drug in the CSF will be roughly equivalent to the unbound concentration in plasma. And not only in CSF, but in brain extracellular fluid as well. But CSF is a easier matrix to measure. So then what are some problems? Because there are issues with highly protein-bound drugs. Well, first of all, what is highly protein-bound? And this really depends on who you speak to, okay? But I'm going to say in the high 90 percentile. Okay, something that's 50, 60, 70% protein bound is not of that major consequence therapeutically, and I'm going to, hopefully you'll be able to understand why as we talk about this. Saturation refers to a situation where once you fill up all the plasma binding sites with drug, any additional increment of drug will tend to be more, have a greater percent of being free and unbound. Okay, once you have enough drug that you saturate the protein binding sites, additional drug will be largely unbound. Okay, that's called saturation. That can happen with very large doses of certain drugs. Another thing that can happen is displacement, where you have drug A bound to protein. Remember, it's a reversible thing. And then another drug B, comes in, and if it binds to the same site on the plasma, knocks out drug A. It's just it's kind of like competitive antagonism in a way. Now, here's the thing. What is the effect of these two situations on the free fraction of drug? Well, if a drug is highly protein bound, say it's 98% protein bound, right? 98%. And it goes from it goes from 98 to 96% protein bound due to some additional drug which displaces some of it. Now, it only went from 98 to 96% protein bound. That sounds like a small change, but yet the free fraction went from 2 to 4%. That's a double. So the actual therapeutic concentrations, okay, the concentrations available to interact with the receptors doubled. That's a big deal, okay? That's why highly protein-bound drugs, we have to be careful, because displacement or saturation can have a major effect on free drug concentration. So this little table basically illustrates what the potential consequences are of high protein binding. Okay, so let's look at the situation where we have saturation. As with dose increases of this hypothetical drug from 5 to 10 to 20 milligrams per kilogram, well, the percent bound first stays the same, and then when you get to this higher dose, you saturate the binding, so you've saturated it. What happens to total? Well, total drug that is bound and free goes up in proportion to the dose. Nothing mysterious about that. But the concentration of free drug, okay, goes up at first in proportional to the dose, and then when you reach saturation, all the additional drug that's in the circulation is now unbound free drug. So you see that for a small increase in dose, we get a whopping increase in free drug concentrations. And since it's the free drug concentrations that matter, that can be a dangerous situation. In terms of displacement, we have, for example, warfarin and tolbutamide, a well-known drug interaction. If you have just warfarin itself, it's about 99% protein bound, okay, leaving about 1%, or let's say for every 99 molecules of bound, you have 1 molecule of free. But how about when tolbutamide is added? Tolbutamide knocks warfarin off of its plasma protein binding site, so that now maybe the percent bound warfarin goes down from 99 to 50, hypothetically, but it does go down. What happens to the total warfarin? Well, that doesn't change. Okay, we've just knocked it off of its binding site, but if you took an assay of total warfarin in blood, that wouldn't change. But look at what happens to free. We've gone from 1 molecule of 99 to 50, okay, unbound and 50 bound. Tremendous increase in free drug concentration. So again, this just illustrates that for highly protein-bound drugs, you have to be careful for saturation and displacement. I think if you just try doing the numbers on your own, you'll see that if you have compounds that are 20-30% protein-bound, it doesn't make such a big difference to have changes in percent free. Lastly, I again do want to encourage you to take a look at Pandit. Very easy read. Chapter 8 on drug distribution will give you kind of a nice additional approach to the things I've said, and hopefully clear up anything that might be a little fuzzy. Okay, that's it for now, my friends. God bless, and shoot me an email if you have any questions.